Have you ever wondered why time seems to fly when you're having fun, but drags when you're bored? It might not be just your perception. According to Einstein's theory of relativity, time can actually speed up or slow down, depending on how fast you're moving and the strength of gravity. Intriguing, isn't it? Now, let's dive a little deeper. Consider this. You're on a car journey. You feel like the trip is taking forever, but for those waiting at home, it seems as if you've arrived in no time. This is similar to the concept of time dilation in relativity theory. It suggests that time and space are not separate entities, but are interwoven into a four-dimensional fabric known as space-time. And here's the catch. This space-time isn't static. It can be stretched and squished by speed and gravity, just like a trampoline under a heavy weight. So just as your perception of time changes based on your activities, the universe also experiences time in a relative manner. You might have heard that nothing can travel faster than light, but have you ever wondered why? Let's take a moment to delve into this fascinating concept. You see, the speed of light is a constant in our universe, unchanging and unfaltering, regardless of where you are or how fast you're moving. Imagine being on a train that's moving at a constant speed. To you, the other passengers appear stationary, even though you're all moving together at the same speed. This is similar to the way light speed operates in the universe. No matter how fast you're moving or where you are, light will always seem to travel at the same speed. It's a bit like a cosmic speed limit, unbroken and unbreakable, a constant that anchors us in the vast expanse of the universe. So, while you might be hurtling through space on planet Earth, light will always seem to travel at the same speed to you. Imagine you're in an elevator. Suddenly, the cable snaps and you start falling. Would you feel weightless? This isn't just a thought experiment, it's a key concept in the theory of relativity. Let's dive deeper into this idea. It's called the principle of equivalence, and it's a cornerstone of Einstein's theory. It suggests that gravity pulling in one direction is completely equivalent to an acceleration in the opposite direction. Here's a way to visualize this. You're in that falling elevator, right? As it plummets downward, you feel weightless. You're not being pulled towards the floor like you usually would. This is because you and the elevator are falling at the same rate. But let's flip this scenario. Imagine the elevator is in outer space, far away from any gravitational pull. Suddenly, it starts accelerating upwards. You would be pressed against the floor, much like you would feel if the elevator was stationary on Earth, right? In both cases, you feel a force acting on you, whether it's the Earth's gravity or the acceleration of the elevator. This is where the brilliance of the principle of equivalence shines. It tells us that these two scenarios are indistinguishable based on the forces you feel. In other words, gravity and acceleration are two sides of the same coin. They are, according to the theory of relativity, equivalent. This principle doesn't just apply to elevators in free fall or outer space. It's a universal concept that we experience in our daily lives. Every time you feel the push against your feet when a car accelerates or the pull of your body towards the earth, you're experiencing the principle of equivalence. You're living the theory of relativity. It's a fascinating concept, isn't it? The theory of relativity, in its elegance, has reshaped our understanding of the universe. It tells us that gravity isn't just a force pulling us down, but an acceleration pushing us up. So, next time you take an elevator ride, remember, you're experiencing a tiny taste of the theory of relativity. So, what have we learned about the theory of relativity? Well, we've delved into some truly fascinating concepts. We started with the relativity of time, exploring how time dilation means time can actually slow down or speed up depending on the speed of the observer. Isn't it amazing to think that time isn't as constant as our wristwatches would have us believe? We then took a journey at the speed of light, understanding that this cosmic speed limit remains constant, no matter the perspective. It's like being on an eternal cosmic highway with one unwavering speed limit. Lastly, we embraced the gravity of the situation by examining the principle of equivalence. We learned that gravity isn't just a force pulling us down, but a curvature in the fabric of space-time itself. Remember, the universe might be more complex than we can imagine, but with a bit of thought, we can start to understand it. After all, as Einstein said, the most incomprehensible thing about the universe is that it is comprehensible.